Hi, welcome to this Elkchemist chemistry video looking at carboxylic acids. This video is going to focus on some key definitions, how we make carboxylic acids, how we name and draw the structures of carboxylic acids, and finally some of the key important reactions of carboxylic acids with various other substances. Now, initially I want to focus on the idea of carboxylic acids being another good representation of a homologous series. The term homologous series is essentially chemistry speak for a family of molecules which have similarities to each other. The key aspects of the definition of homologous series are that they will be a series of molecules with the same general formula. I'll expand upon that idea later. Similar chemical properties to each other based on the fact that members of the family will have the same functional group found within the molecules. A functional group is either an atom or group of atoms that give that particular molecule its chemical properties. Members of homologous series will also have a graduated trend in their physical properties. For example, we'd expect the boiling point of the molecules to increase as their chain length increases. This is due to the increased prevalence of intermolecular forces along that chain, along the surface area of that chain, which need to be overcome, which will take greater amounts of energy to overcome that greater number of intermolecular forces along that increased chain length. And finally, you'd expect successive members of the series to differ from each other by CH2, i.e. each new member of the series will increase in size by CH2, one carbon and two hydrogen atoms in its size. Now I'd like to focus on how we actually make carboxylic acids through chemical reactions. And at this point, it might be worth also recapping just the oxidation of alcohols in terms of complete combustion of alcohols as a nice recap of the alcohols topic as well. Let's take a moment just to consider oxidation as a term before we get stuck into forming carboxylic acids. Oxidation is actually quite a multifaceted idea, and there's many different ways we can look at it to define exactly what it is. We could consider oxidation as the loss of electrons from a particular species across the course of a chemical reaction, as shown by definition part 1. Or we could look at oxidation as the gaining of oxygen atoms by a particular chemical species across the course of a chemical reaction, as shown by definition part 2. And finally, we could look at oxidation as the loss of hydrogen atoms from a substance across the course of a chemical reaction, as shown by part 3. So it can be quite hard to spot oxidation if we're looking for one of these three things happening. And as long as one of these three things has happened, we can be pretty sure that was an oxidation reaction. So coming back to the forming carboxylic acids idea, I've got three areas of investigation. The first actually won't make a carboxylic acid. It's more of an investigation of a quite aggressive way of oxidizing an alcohol through complete combustion of that alcohol. So a bit of an aside. Parts 2 and 3 will generate carboxylic acids through these chemical processes, one involving microbial life and the other using a suitable chemical oxidizing agent. So I'm going to take a moment to talk about the complete combustion of the alcohol ethanol for three reasons. One, it's a good excuse to look back at the alcohols topic. Two, it's a really good excuse to do some balancing equation practice. And three, this is an excellent illustration of an oxidation reaction because when you completely combust the alcohol ethanol, you'll see the product is carbon dioxide. So you can see two of the three aspects or ways of defining oxidation have been shown in this equation because the chemical species has gained oxygen atoms and lost hydrogen atoms to be converted from ethanol into carbon dioxide. What makes this a complete combustion reaction is that it has to take place in sufficient oxygen, in an excess supply of oxygen. If this was not a complete combustion reaction, we would not have formed carbon dioxide and water. We may have formed poisonous carbon monoxide or even some carbon particulates instead of our carbon dioxide and water purely. So this is an example of a complete combustion reaction as shown by the products of combustion. And as I said, a good excuse for some practicing of balancing equations. When dealing with a combustion reaction, you tend to want to take this in an alphabetical order, starting with the carbons, then the hydrogens, and finishing by balancing the oxygens. So let's try that now. I can see 2 carbons on the left-hand side of this equation, hence why I brought the large coefficient in front 2 to multiply the carbons in carbon dioxide up to be 2 as well. Let's now work out the hydrogen balancing. So 3, 4, 5, 6 hydrogens on the left, so I need to have 6 hydrogens on the right. Now the water molecule, H2O, only brought 2 hydrogen atoms, so my coefficient multiplying number 3 multiplies that water molecule by 3. 2 hydrogens times 3 is 6 hydrogens, therefore balancing the 6 hydrogens on the left-hand side, leaving me with balancing the oxygens. Okay, so if I take into consideration that I've got 2 times 2 oxygens on the right-hand side with the carbon dioxide, plus 3 times 1 for the water, that would be 4, 5, 6, 7 oxygens total. 1 oxygen with my alcohol ethanol means that I need 3 times 2, another 6 oxygens with my 3 oxygen molecules to equal 6 plus 1, 7 on the left, and 4 plus 3, 7 on the right. And that would be a correctly balanced equation for this particular combustion reaction. This second example is a method for producing carboxylic acids, but it's not particularly controllable. If you were to leave, say, a glass of wine or a bottle of wine open to the air, or any alcoholic beverage for that matter, bacterium in the air itself, called acetobacter, will actually use oxygen from the air to oxidize the alcohol content, the ethanol in the wine, into vinegar, into ethanoic acid, a carboxylic acid molecule. And it changes the taste of the wine from that sweet tannin flavor to that vinegary flavor, sour in taste. And so you've converted your wine into red wine vinegar, which again is a commercially useful flavoring product. Now, the more relevant example from a chemistry lesson point of view would be to use a chemical oxidizing agent to convert the ethanol into ethanoic acid. And the most common chemical oxidizing agent you guys will be utilizing is going to be sodium or potassium dichromate. And I've chosen potassium dichromate, K2Cr2O7, acidified with dilute sulfuric acid. Now, that reagent will oxidize the ethanol to ethanoic acid. And in the process of doing so, it will change the color of the dichromate ions from a beautiful orange color into quite a dark green color. And that's how you know that the oxidation reaction has successfully taken place. And you need to know that color change. In this video, I'm not going to expand upon the change in oxidation state of the dichromate ions to chromium-3 ions, which results in that orange to green color change, because that would be more suited to an A-level content video, which will be a different prospect. So I'm only going to focus here on the equation I've written. So we've got ethanol reacting with this square bracketed O. That square bracket O represents any oxidizing agent we need it to be. In this case, it represents the formula of K2Cr2O7, the oxidizing agent we're using. Now, why have I had to put a 2 in front of that? Because if I hadn't done so, I would have had ethanol reacting with the oxidizing agent to make ethanoic acid. And of course, that would have been 1, 2 oxygens on the left, and there are 2 oxygens on the right. So why have I had to bring an extra oxygen with the oxidizing agent with that coefficient in front? Well, it's because I had to account for what happened to the hydrogen as well. So ethanol had 3, 4, 5, 6 hydrogen atoms, but ethanoic acid, the carboxylic acid, only has 4. So where's the rest of the hydrogen gone? Well, it's been used to form a water molecule as well, H2O. That therefore means I have 1, 2, 3, 4, 5, 6 hydrogens on the left, and 1, 2, 3, 4, 5, 6 hydrogens on the right. But if I didn't put this 2 in front of the oxidizing agent, I would have had 1, 2 oxygen atoms on the left-hand side, and 1, 2, 3 oxygen atoms on the right-hand side between the ethanoic acid and water. So we bring that large coefficient 2 to multiply the oxygens brought by the oxidizing agent by 2. So we therefore have 1, 2, 3 oxygens on the left-hand side of the equation, and 1, 2, 3 oxygens on the right-hand side of the equation. This is a good example, therefore, of a generic oxidation reaction balanced equation. At this point, guys, I'm going to give my usual spiel about the video's content. If you're finding this video useful, informative, then please do give the video a like, maybe thinking about subscribing to the channel for more content, or even ringing the bell to be notified of that content. Your support for this channel really helps keep me motivated to keep making these videos. Right, now the sales pitch is over what is in front of you right now. This is a grid which explains about the nomenclature of the carboxylic acid, how to name them, and also takes you through a number of key formulae, ways of representing those carboxylic acid molecules. So I want to take you through the key headers to each of the columns you can see. The name of the molecule is the name of the molecule. Mind blown. A molecular formula is the simplest formula we can possibly think of, and it is just the numbers of atoms of different elements found within the molecule itself. A structural formula gives us more information, more detail. It's not just the numbers of atoms of different elements, but also how they're arranged along the molecular structure, where they are, how many around each position of carbon, for example. The displayed formula gives us even more information still. It's not just how many atoms of different elements and how are they arranged, but also what's the bonding within this molecule. Is it a single covalent bond? Is it a double covalent bond? Where is that single or double covalent bond? So you can see that each movement along the column increases the information and opens up the picture of exactly how that molecule is structured. So let's start off with the nomenclature, the naming of this particular homologous series. We've got meth, eth, prop, bute, and it would go pent, hex. So each of those prefixes tells about the number of carbons present within the molecule. Meth stands for 1 carbon, eth for 2 carbons, prop for 3 carbons, bute for 4 carbons, pent for 5 carbons, and hex for 6 carbons. And if you want a quick aide-memoire for that nomenclature system, just think of a monkey eating peanut butter peacefully and happily. Gives you the starting letters M, E, P, B, P, and H. Monkey eating peanut butter peacefully and happily. And it's a great picture of a monkey as well, if I do say so myself. I'm now going to talk about carboxylic acids as acids. And at this point, it's probably worth defining exactly what I mean by the term acid. I'm going to be using the Bronsted-Lowry definition of acids, and that is that all acids are hydrogen ion donators. They release hydrogen ions in solution, and it's the hydrogen ions protonating other chemical species which accounts for the acidic properties of all acids. Now, in the case of ethanoic acid, I'm going to use a monomod kit model to illustrate where the hydrogen ion actually comes from in that molecule. So here's my molecule of ethanoic acid, CH3C double bond O OH, and the hydrogen ion is dissociated, breaks away from the rest of the molecule at this point here. It's the OH group of the COOH functional group which generates the hydrogen ion for carboxylic acids like ethanoic acid. Ethanoic acid is defined as a weak acid, so there must be a difference between strong acids and weak acids. Well, strong acids, like hydrochloric acid for example, they'll be releasing every single hydrogen ion they can into solution. Every single hydrogen chloride molecule will be releasing its hydrogen ions in solution in the water at any one moment in time. Now, imagine for a second that I could stop a solution of ethanoic acid in time and space and investigate every single molecule to see whether it had dissociated, whether it had lost its hydrogen ion or not. What I would find is that 99% of the molecules I investigated would be undissociated ethanoic acid molecules, having not released their hydrogen ions in solution. Only about 1% of the molecules I would find would actually be dissociated ethanoic acid molecules, having released their hydrogen ions, forming the ethanoic ion as well. So we represent this fact by using a reversible symbol and representing the dissociation of ethanoic acid as a reversible reaction, with the equilibrium position heavily favouring or shifted to the left-hand side of the equation. In other words, the vast majority of the ethanoic acid molecules have not dissociated their hydrogen ions. Only a tiny proportion at any one moment in time will have released hydrogen ions, making it a much weaker acid, releasing far fewer hydrogen ions at that particular concentration compared against a strong acid like hydrochloric acid. I'd like to finish by looking at the reactions of carboxylic acids with metals, alkalis, bases and carbonates. I'm going to refer back to the general equations for the reactions of acids to help me do this and make it simpler. So the general equation for the reaction of acids with metals is MASH, which stands for metal plus acid forms salt and hydrogen gas. Now the salt will be pH 7 and therefore a neutral solution will form. Let's take a specific example here. If I took magnesium metal and reacted it with ethanoic acid, I would form the salt magnesium ethanoate and hydrogen gas. Now to make the name of the salt, you take the metal component and combine it with the name of the acid, but you slightly change the ending from oic to O8. And that is the correct name for a carboxylate salt. Finally, the actual equation itself and how I constructed it, including the balancing. Let's get the formulae right first. Magnesium's formula is Mg and it's a solid. The formula of ethanoic acid, ignoring the 2 for the moment, is CH3COOH, and the red H represents the hydrogen, which will form the hydrogen ion which leaves the acid molecule when it reacts. The salt's formula is MgCH3COO2, and our hydrogen gas is H2 because it's a diatomic molecule. How did I get the formula of the salt correct? Well, let's first of all think about what happened to the acid when it reacted. When CH3COOH ethanoic acid reacts, it loses the H plus ion. This leaves the rest of the molecule as a polyatomic negative ion. In other words, it becomes CH3COO minus overall charge. That's called an ethanoate ion. So if I know that that polyatomic ion, the ethanoate ion, has a -1 charge, and the magnesium ion, which forms our salt, has a 2+ charge, how many of the ethanoate negative ions will I need to balance out the charge of the magnesium ion? Have a think about that for a second. Did you get it? That's right, it's 2. Why? Because 2 -1 ions will perfectly balance out 1 + 2 ion. So the correct formula for magnesium ethanoate is MgCH3COO brackets 2, because I need 2 of the ethanoate ions to every 1 magnesium according to my working for the formula here. Now the balancing. I can't have made 2 ethanoate ions from 1 ethanoic acid molecule because it won't balance out. I haven't got enough of the ethanoate section to produce 2 of them in the magnesium. So I put a big coefficient multiplying ethanoic acid by 2 to allow me to bring enough ethanoic acid to actually make the correct formula for my salt, but also I need to release 2 hydrogen ions if I'm going to make H2 gas. So that helps to ensure that the same number of atoms on the left-hand side and on the right-hand side of this equation. Number 2, the reaction of acids with bases. What is a base? A base is a substance which can neutralize an acid but is insoluble in water. A good example of these will always be metal oxides. So my general equation, acids react with bases to form salts and water. So the salt will be a pH 7 neutral solution when it dissolves in water, and water is itself pH 7 and a neutral liquid. So my example, methanoic acid reacting with calcium oxide to form calcium methanoate and water. How do I generate the name of the salt? You take the metal component from the base and bolt it on to the name of the acid, except you change the ending from oic to O8, and you have correctly named this particular salt, which is calcium methanoate. Now on to the equation. Here is the formula of methanoic acid, HCOOH. Calcium oxide is my base. Calcium methanoate is my salt, and water is the other product. How did I get the correct formula for this salt? Well, as last time, the hydrogen ion from methanoic acid is lost. That's the H plus ion leaving, and it leaves the rest of the original acid molecule as a polyatomic negative ion, the methanoate ion, HCOO-1. So, how many -1 methanoate ions will I need to totally balance out the 2+ ionic charge of the calcium ion of our salt? I would need 2 -1 methanoate ions to cancel out the charge of a calcium 2+ ion. Hence why the formula is Ca brackets HCOO close brackets 2, because I need 2 of the -1 methanoate ions to every 1 2+ calcium ion to create that formula. Finally, balancing the equation, you'll notice that there are 2 methanoate ions on the right-hand side, so I'd need 2 methanoic acid molecules to generate those 2 methanoate ions. So I had to bring a large coefficient multiplying 2 number to multiply methanoic acid by 2 to ensure I could produce my correct formula on the right-hand side. Also, you'll notice that I couldn't have made water H2O if I didn't have 2 hydrogen ions coming from 2 methanoic acid molecules at the start. And this is a balanced equation because there are the same number of atoms of different kinds on the left-hand side and the right-hand side of this equation, so it all balances out really nicely. Number 3, the reaction of acids with alkalis. And what is an alkali, I hear you cry? Well, an alkali is a substance which can neutralize an acid, but which is soluble in water. Unlike bases, it will form solutions. So in my general equation, we have an acid reacting with an alkali to form salt and water. Again, as last time, the salt will be pH 7 neutral solution and the water is a neutral liquid. My example, we have propanoic acid reacting with potassium hydroxide, my alkali. The OH minus ions from the potassium hydroxide are the alkali components, forming our salt, potassium propanoate. Again, take the metal name from the alkali and the acid's name, propanoic acid, remove the OH and replace it with O8 and you have the correct name for the salt, and water is formed. The balanced equation, there is the formula of propanoic acid. Again, I've highlighted the hydrogen ion being lost as the red hydrogen at the end of the molecule. Potassium hydroxide, the OH, is the alkali component which will go on to form our water. And then the name of the salt, how do I get the formula of the salt, which is KCH3CH2COO all together? Well, you take the positive potassium ion, and if we lose the hydrogen ion from the propanoic acid, what's left is the polyatomic ion propanoate, which is CH3CH2COO minus. If you add a -1 ion, it's going to balance out perfectly with a +1 potassium ion, because it's a group 1 metal, and therefore the formula would be fine as being KCH3CH2COO, because it's a +1 ion balanced off against a -1 ion from the propanoate ion itself. So it's a balanced equation because we have the same number of atoms, different kinds on the left and the right, and that's our third equation out of 4. Finally, we have number 4, the reaction of acids with carbonates. I'm kind of stretching the general equation beginning letters thing a bit here, but we have an acid reacting with a carbonate to form salt, water, and carbon dioxide gas. Again, the salt will form a neutral pH 7 solution, water is a neutral liquid, and carbon dioxide gas is carbon dioxide gas. The example, ethanoic acid, vinegar, reacting with zinc carbonate, a metal carbonate, to form zinc ethanoate, a salt, and water and carbon dioxide. Getting the name of the salt right, take the metal component from the carbonate, the acid's name, replacing oic with O8, and you've made the name of the salt. Now the balanced equation and the formulae. The formula of ethanoic acid is CH3COOH. Again, I've highlighted the hydrogen which will be lost as a hydrogen ion in red. Zinc carbonate, I've highlighted the carbonate ion, the CO3 2- ion as the sort of blue colour here. Zinc ethanoate, the salt, plus water, plus carbon dioxide. How did I get the correct formula for zinc ethanoate salt? Well, again, if we lose the hydrogen ion from the ethanoic acid molecule, what's left is the polyatomic ethanoate negative ion, CH3COO minus. If it's a -1 ion for that ethanoate ion, how many would I need to balance out the charge of a zinc 2+ ion in the salt? I would need 2 -1 ions to balance out the 2+ charge of the metal ion. So the correct formula for zinc ethanoate is Zn, then open brackets, CH3COO, close brackets 2 -1 ethanoate ions to every 1 zinc 2+ ion. And finally the balancing. Well, again, I can't make 2 ethanoate ions inside the salt without having 2 ethanoic acid molecules to bring those ethanoate ions. So I put a large coefficient 2 in front of the ethanoic acid to multiply everything by 2 to bring 2 ethanoate ions. And again, that brings 2 hydrogen ions, which accounts for the fact that water is H2O. And that will mean I have the same number of atoms of different kinds, different elements on the left-hand side and the right-hand side. So it is a correctly balanced equation. And you have just written 4 complex carboxylic acid-based balanced equations really well. So you've made it this far, guys. Well done. You've just completed the full tutorial on carboxylic acids. Again, thank you so much for listening. And if you found this video useful, please do give it a like. Maybe think about subscribing to the channel, and do check out other videos which will appear here for other recent content on organic chemistry. And I'll speak to you guys soon. Thanks very much. Take care now. Bye.